In this segment, we're going to talk about air standard assumptions and cold air standard assumptions. So we've got these ideal cycle assumptions. We got 3 of them. And when we talk about gas power cycles, we're going to make a few more assumptions that are specific to gas power cycles, and those are called air standard assumptions. First assumption of air standard assumptions is that we've got air as a working fluid and it behaves as an ideal gas. So we have several forms of the ideal gas law that we can use. That R is the specific gas constant. It's specific to whatever gas that you're talking about. You can calculate it based on the universal gas constant, R bar. So that universal gas constant, it's at the very bottom of the page that has all your conversion factors on it. And that's in that thermodynamic tables packet that is on Canvas that's available to you as well. For air, this works out to be 0.287 kilojoules per kilogram K. So you get that by dividing the universal gas constant divided by the molar mass. You can also calculate that in English units if you'd like. If you need a review on ideal gases, please review the Thermo 1 video on ideal gases. So what this also means is that for an isentropic relationship, you can use, or for an isentropic process, you have isentropic relationships for ideal gases that you can use. So isentropic means that it's reversible and adiabatic. And if you look at those ideal cycle assumptions, it says that all processes are reversible and that you have no heat transfer where you don't want it to occur. It doesn't mean that there's no heat transfer whatsoever in that cycle, but during the processes where you don't intend heat transfer to occur, there isn't any heat transfer. So you will have isentropic processes, and because you've got this ideal gas, you've got those isentropic relationships that you can use for an ideal gas. And these are the ones that deal with the relative pressure ratio and the relative specific volume pressure ratio. And if you need a review on those isentropic relationships, please do look at the review video for Thermo 1 on isentropic relationships for ideal gases. All right, so you've got working fluid, it's air, it's treated as an ideal gas, that's number 1, and number 2 is that all those cycles are internally reversible. So that's kind of mirroring number 2 in the ideal cycle assumptions, but nevertheless, what that essentially means for us is that when we evaluate boundary work in a closed system, we can use this equation right here, that the work is equal to the integral of PdV. This is an equation that we can use if we assume that everything is operating in a quasi-equilibrium manner. If we have an open system, we have an equation for steady flow reversible work, and that would be the negative integral VdP. All right, and then the last air standard assumption is that all combustion processes are modeled as simple heat addition processes, and all exhaust processes are modeled as simple heat rejection processes. Combustion is a pretty complex phenomenon. We'll spend some time talking about that towards the end of the semester. But what we need to know now is, in reality, you've got a combustion chamber, you've got air coming in, fuel coming in, there's a combustion reaction, and what comes out are the products of combustion, which are not air and fuel anymore. So what we're going to do is we're going to simplify things, and we're just going to consider a heating process or a heating section within our cycle, and say that we've got air coming in, and then we add some heat, and then it comes out, same air, it comes out at some higher temperature, and that's it. And then the same thing, you could flip it around for the exhaust process. You have a Q out instead of a Q in. All right, so we've got these air standard assumptions. We can make one more simplifying assumption, and if we did that, what we'd call that set of assumptions would be cold air standard assumptions. So cold air standard assumptions takes into consideration all 3 of those assumptions for the air standard assumptions, and it adds a 4th, which says that the specific heats are assumed to be constant. Specific are assumed to be constant. Specific heats are assumed to be constant. And these are taken at 25 degrees Celsius, or about 300 Kelvin. For air, you can look up in table A20, I believe it is. This would give you CV is 0.718. CP is 1.004 kilojoules per kilogram K, and K, which is the ratio of CP over CV, is just equal to 1.4. So what this means, if the specific heats are assumed to be constant and you have an ideal gas, any delta U's can be approximated as CV delta T's, and any delta H's can be approximated as CP delta T's. If you happen to have an isentropic process, that also means that you can use isentropic relationships for an ideal gas with constant specific heat. So instead of using the ones that have relative pressures and relative specific volumes, you can calculate temperatures and pressures and specific volumes at the end of that isentropic process, and you don't have to look up anything in those ideal air tables. So, all right, well, I hope that was helpful, and thank you very much for watching.